Thanks very much, everybody, for taking your valuable time and coming to this briefing on Landsat entitled Fire, Food, and Water, 40 Years of Landsat Satellites. We're here today basically to highlight and to celebrate some of the significant scientific advances and the societal benefits that have resulted from combining Landsat measurements with a host of focused research investigations over the past 4 decades. Earth, this planet that we live on, is actually a pretty complicated place. There are many, many different processes which are going on simultaneously and continuously, and the processes themselves are interacting with each other. If we are to understand the Earth as a system, it's not enough to simply diagnose and measure individual processes, but rather we have to understand how the processes interact, the interactions between them, and to make scientific progress towards that understanding, to monitor our planet, and to detect the subtle trends in the face of sometimes large seasonal and other short-term variability. We have to make measurements on a wide range of scales. From a spatial standpoint, we have to make measurements on scales from a few tens of feet through thousands of miles, indeed around the entire globe. And we have to make those measurements over long time scales, but resolving short-scale variability, so making measurements from days to decades. And it's the vantage point of space that really provides the only approach for making these measurements in their entirety. Landsat has used high-quality instruments mounted on Earth-orbiting satellites in service to science and humanity. The Landsat program has produced, not only for this nation, but for our entire species, the longest, continuous, accurate, consistently processed data set ever obtained from space. Since this date, today, July 23rd in 1972, Landsat satellites carrying high-quality instruments, infusing evolving technology over the decades where they're appropriate, have maintained basically a constant vigil over the Earth, tracking how our planet is changing and how we are changing the planet. With the launch of the NASA USGS Landsat Data Continuity mission this coming February, the data set is going to be extended even farther into the future. Importantly, by making all of the Landsat measurements and the derived information products freely available, many scientific and societal benefits have been achieved that were not really identified or even conceived of at the start of the program. The nation, and indeed the whole world, has redeemed our investment in Landsat measurements and research many, many times over. So, turning to the panel, our speakers today are 3 of the most distinguished representatives from among the whole host of leaders who have contributed to Landsat analyses over the decades. First, Chris Justice, who will speak to us about Landsat and fires, is professor and chair of the Department of Geographical Sciences at the University of Maryland. Phil Rasmussen, who's going to speak on food and agriculture, is the director of the Western Regional Sustainable Agriculture Research and Education Center at Utah State University. And Matt Larson, who's going to be discussing Landsat contributions to water monitoring, is the associate director for climate and land use change at the U.S. Geological Survey.
So this presentation is the first 40 years of Landsat, because I believe there needs to be a second 40 years of Landsat. It has a very interesting history. If you go back and look, it moved from the government operation to commercial and back to the government, where I believe it truly belongs. And that we see the program has evolved in the digital age. The first products that I used were 70mm film products. We made photographs and did photo interpretation. Now we're downloading gigabytes of Landsat data. The whole system has evolved together. My thinking about this 40-year celebration is, could those who designed and launched the first ERTS-1 system in '72 have imagined that 40 years later, the program would be about to launch the next in the mission, and providing data that's critical for the science of the 21st century. So what is that science? I work in part with Garrett Gutman here from NASA on the Land Cover Land Use Change program, and Landsat is the instrument of choice for that program. The Land Cover Land Use Change is happening around the world, driven by economic development, increasing population, and climate change. And we're trying to understand the drivers and the impacts and the consequences, leading us to a better understanding of human interaction of the land surface and the future of adaptation, sustainability, and resilience of these land use systems. Perhaps the most iconic image is this one from Rondônia, Brazil, that everybody's probably seen, but it gives us an idea that this is tropical forests, and using the archive of Landsat, we're being able to look at what happened when the expansion out to the west of the country opened up agriculture and started to clear the forest. This is 89. This is 2001. Translating the forest into agriculture, subsistence, and then into ranching. So why do we care about deforestation? Deforestation, particularly in the tropics, plays an important role in the carbon cycle, and nations need to quantify and report their rates of deforestation. We can use Landsat data to look at very, very large areas. This is the Congo Basin, quite inaccessible in parts, but we're able to monitor, using this system, the changes, this from 1990s to 2000s. And in detail, you can see the areas in red are where you're having agriculture expanding into the areas of tropical forest. We can do the same in Southeast Asia, but prior to 2008, we were obliged to use small amounts of data and to look at epochs, look at areas that have changed from 2000 and compare those to what was the situation in 1990. So in 2008, the USGS opened up the archive, and if you look at the plot on the right-hand side, you can see what happened. The use of data was exponential. It's gone up, and combined with our ability to process and analyze the data with the computation capacity, we've had a major change in the way that science is done. So here's an example from Indonesia. This piece of work by Matt Hansen used 15,000 Landsat scenes to produce the forest cover loss between 2000 and 2010. Looking at this area in the box here, we can see in detail the area of forest cover change. But not only can we see the total change, but if we start to use data from every year, we can map the progression of the deforestation. 2005 and 6, 7, and then 2008. And we can start to look at the trends in forest cover loss on an annual basis, which is exactly what's needed for national reporting. We don't just have to work in the tropics, we can work in the US, and we're starting to use the archive of data to develop long-term record of disturbance of forest. You can see this for part of Virginia. This is northwest of Richmond, an area of rapid change due to plantation forestry. And start to look at how the forests of the US are changing over time. This is comparing the Olympic National Park, clearly very little change as compared to Mississippi. And the bottom there where you see a progression of change and the history of disturbance. So one of the most common forms of disturbance to the forests of the US is through wildfire. And here's the canyon fire from Colorado Springs that we've been hearing about in the news. And you can see the dark patch there of the burned area. And this was a shot that was taken of that forest fire from the ground, quite spectacular. Why do we care about forest fires? Because these are an important source of trace gas emissions, and nations also need to estimate the area burned and the associated emissions from fire. So there's an ambitious project run out of the USGS mapping the record of fire since 1984 using the Landsat record. You can see this monitoring of trends in burn severity project produces national estimates of the area burn. But this is a very time-consuming and laborious exercise, looking scene by scene and mapping burned area. So what we need to do now is develop tools for quick analysis of large areas. This is a project run by David Roy from South Dakota State, who's developed the same kind of approach we've been taking for coarse resolution data to Landsat. This has involved over 8,000 acquisitions and produces a mosaic that can be used for mapping. Here's an automated classification method that we've been developing in our group, taking those data and applying a very physically based, simple, very quick method for classification of those imagery. If we apply that to the burn severity mapping, we picked an area here out west there, and you can see there's the well tile. This is the Landsat data that's been mosaiced. This is a composite for the summer 2002, and you can see for the fall of 2002, the burned area. If we apply our automated classification to that, you can see the area that's burned by time. The colors represent the change from June through to October, and you can see the area that's burnt. And then if we compare that to the MTBS, you can see we've got a very nuanced automated approach for mapping burned area. The exciting thing is now we have a system that can produce products at the global scale from Landsat. This is truly amazing. I think those of the people in the room that saw the first Landsat images come through never imagined that we would have this capability. And I think now you can imagine applying a global burned area mapping system, automated, to this system. So there's a lot of remarkable things about the Landsat program. This is a slide that I got from Sam Goward, looking at the original 1970 plan for advanced Earth resources satellite. Over on the left-hand side, the column there, the spectral bands, and then you can look and see what happened in the terms of the thematic mapper. And it shows there was a keen understanding of what is needed to monitor vegetation at that time, back in 1970. When you look at the next generation being built now and ready for launch next year, early next year, you can see that it hasn't changed very much. We've got the model right for how we monitor vegetation. Another remarkable thing is Landsat 5. The thematic mapper was suspended in May of this year, but the multispectral scanner is still operating. This is 28 years, a nominal life of 5 years. It's a testament to the skill of the engineers that build these instruments. This is quality engineering. And another remarkable thing is that despite a major instrument failure, it's taken us 10 years to launch another instrument. Okay? And it's worth noting that India has launched 9 Earth observation satellites since that time. So I think this gives us a lot of food for thought for the future. Also, the 16-day repeat coverage of Landsat, which is what we had in 1972, remains the same. If you live in the area where the circle is and you want to get clear observations to see what's going on in terms of the agriculture, for example, you would have to wait 2 months to get a clear image. So we need more frequent imaging if we're going to look at rapidly changing phenomena such as fire, flooding, and agriculture. If we combine satellites from different systems, this is the LDCM combined with data from ESA. ESA is going to launch 2 Landsat-like instruments in the next 5 years. If we combine those together, you can imagine then that we would have coverage on the order of 2 days. So 2 to 3 day coverage at this scale, which would give us what we need for the future. So here, in summary, is my summary points. I think that the Landsat program is as vital as transformative today as it was when it was launched 40 years ago. I think we're seeing new capabilities develop based on our compute and the free and open sharing of data. This is fueled by NASA's investment in R&D associated with Landsat and by the open data policy. I think it's a critical tool for Earth system science, quantifying, understanding global land cover, land use change. And the Landsat data record must be continued beyond Landsat 8. So what happens if Landsat 8 goes the way of Landsat 6? We're going to be in a very bad situation. Nobody questions why we need operational weather satellites. I think we need to have a similar operational status for Landsat observations. We ought to think about reduced mission costs and increasing number of instruments flying and ready to fly when one of these instruments breaks. The US should continue to show the way in terms of open satellite data policy for public good. And we need to continue to develop the smart automated tools to exploit these large volume time series data sets that we have now. So today, especially today, we should celebrate the success of the program and recognize the vision and the skills and the insights of all those who designed, developed and built the missions. Some of those are actually in the room today. At least I see one of them. And we should also consider how we can regain U.S. leadership in terms of this moderate resolution Landsat class remote sensing. Thank you very much.
Okay, as I said, my name's Phil Rasmussen. I'm better known as No-Till Phil out in the West because I've done a lot of work with what we call no-till farming, which is trying to reduce the amount of plowing that we do and decrease soil erosion. But I'm going to talk about the Landsat satellite series in terms of food because it's extremely, extremely important. And I'm going to tell you a little bit about myself as well. As I mentioned, my name's No-Till Phil. I've done a lot of work with farmers and ranchers in the 13 western states as well as the islands of the Pacific that have land-grant schools in our American protectorates out there in Guam, Micronesia, Northern Mariana Islands, and American Samoa. And so I've gotten to see agriculture from a broad paintbrush that the West represents all the way from Arctic tundra to the Mediterranean climate of the inner California valleys. But sustainability is the key. One of the things that we're worried about is making sure that we have the capability to produce food in 20 years or 50 years or 100 years, just like we have it now, and in fact to enhance our ability to produce food for the many more people that will be upon the earth. Now they say young men speak of the future because they have no past, and old men speak of the past because they have no future. I know where I sit in this, and I cannot help but speak of the past just a little bit to give you a little bit of insight to where I'm coming from on this. As an incoming ROTC second lieutenant in the Air Force in July of 1972 at Vandenberg Air Force Base, I was training there, and they rousted us out of bed at 4 a.m. and said, "Come, you're going to see a satellite launch, the Earth Resources Technology satellite." I remember going out there as a college student. I was in my junior year at the university, and like many of the interns that are around here, and I remember all I could think about was how many different languages were being spoken around me as we watched the launch of that satellite from the various scientists from around the world that thought that was going to be the greatest thing since sliced bread. Little did I realize how that was going to impact my career, because I thought I was going to spend my career in the Air Force, but the Vietnam War ended and they decided they didn't need me anymore. And so I went to graduate school, and I went to Kansas State University, and lo and behold, I was funded by a program called the Large Area Crop Inventory Experiment, or LACI, and I spent my days in getting my PhD for 3 years working on predicting wheat yields in western Kansas, where we had big enough fields with the resolution of the satellites that we had at that time, Landsat 1 and 2, that I could get a pretty good definition of what those wheat fields were doing. Little did I realize the CIA was using my equations at that time because the big Russian wheat deal had happened just prior to that, and they wanted to know how much wheat Russia was going to be raising over the next 10 years because it was strategically important. But we found that we could predict the wheat yields with about 95% probability using Landsat information coupled with an evapotranspiration model. And we did quite well because of a couple of physical things in our Earth and in the biological systems that are very important to Landsat. One is that green leaves of actively healthy growing plants reflect near-infrared radiation almost perfectly. And the other thing was that the leaves of plants, the minute that they sense water stress at all, the temperature of the leaf will start to climb above ambient temperature. Usually they're about 2 degrees Fahrenheit below ambient temperature because of the water that's evaporating from them. And so if you have a thermal imaging system, which the later Landsat satellites had, we could tell when that crop was under water stress. Same thing works in a golf course. They often use the new infrared temperature guns like the ones that you can stick in your child's ear to measure the temperature. And you can go out and tell when a plant is water stressed before you can ever see it with your own eyes. And that's an amazing thing. Two things. Green plants reflect near-infrared energy almost perfectly, and actively growing leaves are 2 degrees Fahrenheit below ambient, and when they're water stressed, they climb above ambient temperature. Okay, so we decided to put this to use when I got to Utah State as a new professor. We thought that the new handheld computers were the hottest thing, and so we started to put Landsat information on handheld computers, the same thing that most farmers and ranchers that are using what we call precision agriculture techniques are doing now with their smartphones. They download that satellite imagery, and it helps them diagnose what's going on in their fields. And we'll talk about that more in depth in just a minute. And it doesn't matter which type of smartphone you have or which type of tablet computer. We're using in the classes I teach at Utah State iPads right now. They work great, but so do a whole host of other handheld devices. But the key thing is that we can now hold in the palm of our hand the ability to download and analyze satellite-based information in our hands. And a farmer can do it as he's riding his tractor through the cell phone, which is something that they are doing. You may not believe it, but boy, I've seen it in the growers that I've been working with. Same thing with ranchers, because they can look at the condition of the range and tell just how many animals they can put out on the open range by looking at satellite imagery to tell them just how much rangeland there is there. Okay. So we started training farmers and ranchers and county extension agents on how to use geospatial imagery, and we called it On Target because precision agriculture, GPS-controlled tractors that keep them driving a straight line. My dad would have loved that if we had that technology. So he used to scold me like you wouldn't believe when I had crooked lines when I was seeding wheat. But now GPS-controlled tractors can apply the right amount of nutrients in the right place at the right time for highest yields and environmental benefits. Now, sometimes things don't go quite as you plan. This is a group of county extension agents from across the United States that came to Salt Lake City for some training just prior to the Winter Olympics being held in Salt Lake. We gave them a handheld computer and some Landsat imagery and told them to find the center of downtown Salt Lake City, where there is the prime meridian, as they call it there, that everything in Utah and a lot of the Intermountain West was surveyed from. The problem was we had one county agent who had a really new, accurate GPS system in a backpack. You'll see him over there on the right side of the photograph. Just had to take that with him. Okay, remember, this is right after 9/11. It's in October, just before the Olympics are going to be held in the following January in Salt Lake City. He got to downtown Salt Lake City and was tackled by 5 plainclothes police officers who thought he was laying out a bomb run for the Olympics. But it was just a local county extension agricultural agent that got a little overzealous with his hardware. If he'd have used the handhelds we gave him, he'd have been fine. But there are innumerable applications in agriculture for Landsat imagery. And this is a list that my good friend Ed Scheffner, who's now at NASA Ames Laboratory, put together. There is the crop production forecasting that I was involved in my PhD work, and that's extremely important now to the USDA Agricultural Statistics Organization that plots the amount of wheat, the amount of corn, the amount of soybeans, etc., that are going to be planted and that are going to be harvested, and that literally has a huge impact on the world price of the major commodities. There's monitoring and managing crops. We're going to talk about stress detection, as I mentioned. Remember that? 2 degrees higher in temperature if it's under water stress, and a near-perfect radiator of near-infrared radiation, except when it's under nitrogen stress. And measuring water use in plants, generalized models of evapotranspiration and yield, etc. That'll be talked about in just a moment. Monitoring and managing carbon sequestration. And of course, drought right now is extremely important. And fighting crop insurance fraud and risk management fraud. Okay, let's get a little bit more specific in the managerial uses of Landsat and the imagery that takes place. I mentioned putting nitrogen fertilizer, the major fertilizer that's applied to almost every crop in the United States at the right time, in the right amount, and the right place is extremely important. So we decided we were going to test that with satellite imagery so that we could manage soils, not fields, because as some of you know, you may have a field that's a quarter section, like the big center pivots, and it may have 5 different types of soil types in there that each need a different amount of fertilizer. And so we wanted to manage soils and not fields. And so we got together with the National Organization of Wheat Growers and decided to utilize Landsat information that also feeds into the soil surveys. And I'm going to skip on just a minute and talk about this. We worked with Dwayne Grant in Idaho, who grows potatoes one year and wheat the next year, every other year. And he lost money every year he was raising wheat. But he has to grow the wheat to break the disease cycle in the potatoes. And he said, isn't there some way you can help me to make money with that spring wheat? And we said, yeah, we could make it so it has a higher protein. And so we put out some plots in his field and intentionally induced nitrogen stress. You can see it as a big line going vertically there, and then half nitrogen stress just to the right of it. You can see that line going through that center pivot. And what we found out is you couldn't see it when you go out in the field and look at the wheat, but the satellite could see it, and it told him where he needed to put the fertilizer on and how much. Right time, right place, right amount. And instead of getting $6.60 a bushel for his hard red spring wheat, he got $8.20 a bushel because it went from 12% protein to 16.5% protein with that application of nitrogen that was prescribed by the Landsat satellite. Now there's something you can take to the bank, because high protein wheat is needed to make bread that rises, or you're going to have a very short bread loaf. And so the bakers pay a premium for that wheat, and he was able to get it with Landsat information. And the same thing happens on a lot of other crops, but bottom line, we want to have sustainability while making a profit. So you don't turn out like this photograph above that Carl Coopers from Spokane, Washington, there on the bottom, told me, I want you to remember what I think of university professors. He says, you're always looking in the wrong place at the wrong problem. And using Landsat information is the right thing at the right time in the right place, and we need that data continuity mission to carry that forward. Thank you.
So I'll talk a bit about water resources management as based on Landsat applications. We've heard a little bit from the other speakers. I did want to also, however, acknowledge some of the input from other sources, from University of Idaho, Idaho Department of Water Resources, from USDA, and also from Eros, from Tom Loveland, who's here in the audience. Where are you, Tom? Wave your hand. So thank you for your input into this talk. Now, I'm not going to talk about all these issues, mostly the first one or two on this list, but I think it's important to note the phrase at the bottom, which is you can't manage what you don't measure. And Landsat is one of the remarkable tools we have in our arsenal in the federal government to help measure and monitor various substances, in this case water, and inform the users of that commodity. If we take a flight across the country, you've no doubt looked out the window at one point or another and seen this view, and you probably thought they were magical crop circles created by aliens. But in fact, it's something that's been evolving since the 1950s when center point irrigation was developed. It's a remarkably efficient way of getting water out of the ground, out of groundwater and to the surface, but it has created new problems with respect to water rights, and you know that that's a particularly contentious issue in the West. Water for irrigation is the single biggest consumer of water in the U.S. and, for that matter, in most of the world. So there's a strong need to better manage water so that multiple needs can be met. including ag, of course, but also ecosystems, municipal supply, industry, and the cooling of power plants. Evapotranspiration is a key component in our understanding of how much water is consumed when we irrigate fields. So evapotranspiration, or ET, is that part of the hydrologic cycle when water evaporates or is transpired by plants, and we heard a bit about that from Phil. This is simply when water moves from the Earth's surface back into the atmosphere. Now, scientists use something called energy balance modeling to characterize that, and a thermal infrared sensor shown in this cartoon on a Landsat satellite is used to measure ET as part of that energy balance. Historically, the simplest way to make that type of measurement was to see how much water evaporated out of a pan. And for many years, that's what the Weather Service reported. Later, more sophisticated methods were developed, but all of them have a limitation in that they provide a single point measurement of evaporation or evapotranspiration. And they may not necessarily be representative of a large area like a farmer's field. In contrast, every time Landsat transits the Earth, the satellite collects data for about a 115-mile wide swath, so a large area. Using this Landsat data to estimate ET is transforming this field. It saves labor, it increases the consistency, quality, and repeatability of the measurements, and does so across large areas. So this view shows a Landsat-based evapotranspiration estimate for irrigated region in Idaho. Areas colored in gray have relatively low, gray and tan have relatively low amounts of ET, whereas those in green are transpiring much larger amounts of water, and you can see the scale there on the right. Researchers at the University of Idaho and the Idaho Department of Water Resources used the Landsat thermal infrared sensor to measure evapotranspiration. And they developed a mathematical model called metric to estimate ET at the field scale. This model yields precise and reproducible estimates. Here are infrared images of the same location in the western U.S. showing the differences in resolution between a Landsat image and a MODIS image. And you can see the scale at the top of the image. You can see the importance of the higher resolution that Landsat provides in determining ET at the scale of individual fields, showing here details of center point irrigation. I said earlier that metric provides precise and reproducible estimates of evapotranspiration. The metric model output can tell us how much water is being used in a single field. Other techniques, such as measuring how much electricity is consumed by a well pump as a surrogate for the amount of water that's being brought up to the surface and distributed over a field, are used. But these techniques, and you can see the various estimates on the right side of the image, overestimate water use, and they lead to contention, potentially to court battles between individual landowners or between states over estimates of how much water is actually being consumed. The value of the metric model has been recognized as an important contribution to improved water management. And here we're seeing an award ceremony. The Ash Institute at Harvard University cited Idaho's original design for these maps as an outstanding innovation in American government in 2009. This use of Landsat is not only innovative, but highly practical, as I hope you've gathered from my previous slides there. According to the Western States Water Council, Landsat-based approaches to measuring evapotranspiration are being used in most Western states to improve water resources management. So let me close with just 2 slides about what lies ahead. You heard our previous speakers talk about the importance of Landsat and continuing this mission and this remarkable 40-year effort into another 40 years or more, and I hope we can all be back to celebrate year 80. So Landsat 8, or LDCM, Landsat Data Continuity Mission, as we call it, is scheduled for launch in February. And here are some improvements that Landsat 8 will bring. We're looking at a few more precise bands and narrower bands, so we'll have a better signal-to-noise ratio. There will be better cartographic accuracy. in this new instrument. We'll also be collecting more images on a daily basis, from 250 up to 400, and we'll see some improvements in the panchromatic band spectral range. Specifically for water, the addition of a second thermal infrared channel provides temperature measurements that will improve our ability to quantify ET. This will overall improve our ability to assess water flux from irrigated surfaces. And there's an additional band, something called the Cirrus band, that will improve image quality. It'll allow us to do a better job at recognizing and screening out clouds. And then finally, a new what we call coastal aerosol band, will allow detection of water column constituents, things like chlorophyll, suspended material, and CDOM, which is colored dissolved organic material. That's the optically measurable component of dissolved organic material in water. So these are just a few examples of what we'll see in Landsat 8, and every time we mention it, we knock on wood for that February launch, and I thank you for your time.
My name is Chris Justice. I'm chair of the Department of Geographical Sciences, University of Maryland. So I was asked to talk a little bit about the science, and I was given the topic fire and forest. So for mapping fires, you can use Landsat data quite well after the fire event. We call those sort of burn scar mapping. For forests, you can monitor changes that are taking place in terms of deforestation, selective logging, changes to forests, and try to explain why those are important scientifically in terms of their role in the global carbon cycle, and for fires, for example, in terms of trace gas emissions and air quality. I tried to pick a couple of sort of iconic images, and I think the first was really that Rondônia image from Brazil, which really got people thinking about land use change in tropical forest areas, going back to 75 and looking at the expansion of agricultural land at the expense of tropical forests, and got people thinking about the impacts on biodiversity and water quality and sustainability of those agricultural systems, which really started off as subsistence systems. And the next image really was to then think about doing that at the whole of the Amazon basin scale, and there was some very early work by Dave Skoll from Michigan State, Jim Tucker from Goddard, and myself looking at sort of changes for large area changes. But at that time we were using very little data, and we had to buy the data, so we were very limited in terms of the cost of data. And yet they were able to develop maps of deforestation for the whole of the Amazon basin. I think that would be another iconic image. And then that most recent one from the Weld product from David Roy, where we're actually looking at processing of global Landsat data in the same way that we process moderate resolution or coarse resolution from MODIS. And that really, for me, has been a game change in terms of how we think about Landsat. It's no longer just a single image for a single location. It's a global data set for global analysis at the resolution for land use change that counts. From my side at the moment, I think we should target areas where we're going through rapid land use change, keep going on the tropical forest, but also start to look at the expansion of agricultural lands and start looking at agricultural monitoring. But to do that, then we'll need high temporal frequency Landsat. So the idea of stepping up the acquisition would be good. So that would be a real boon. But I think if we have a science quality instrument and it's free and openly available, then the world will use it, and I think it'll help a lot in terms of some of the monitoring that we're trying to do. And I think there's this idea that, we have to do the next best thing, but we also need systematic, basic monitoring. It's not very exciting in terms of the engineering, but it's absolutely critical in terms of the science that we're doing.
My name is Phil Rasmussen. I'm a professor at Utah State University, but I'm also director of the Western Sustainable Agriculture Research and Education Center at Utah State. I'm probably one of the older people that spoke today. I was old enough to actually be at the Landsat 1 launch when I was training to be an Air Force officer. And so in July of 1972, I was able to see the Landsat 1. It was called the Earth Resources Technology Satellite at that time. later changed to Landsat. But I was able to see that launch. But I didn't realize it was going to have a major impact on my career, because after my brief stay in the Air Force, I went to graduate school at Kansas State University and worked on the experiments that contributed to the large area crop inventory experiment, which actually was predicting wheat yields across the United States using Landsat data. And my PhD research helped predict wheat yields to about 95% accuracy in western Kansas. But I didn't know at the time that the State Department and CIA were also using my equations to predict the wheat yields in Russia at the time, which was strategically important. Well, the most important part is that there's been at least one Landsat satellite operating for 40 years. And so there's a continuous data stream available from the Landsat satellite series that just isn't available anywhere else. So we can look at changes on the Earth's surface that have taken place with time that's just impossible with other satellites. But my particular interest is more instantaneously looking at things with Landsat to determine crop health and crop yield. For example, in a center pivot irrigation system in southeastern Idaho, we were able to use satellites such as Landsat and other satellites to look down in the near-infrared bands and tell exactly when the wheat was nitrogen stressed. And in so doing, we could tell the farmers and ranchers when to apply nitrogen fertilizer to get maximum protein for the wheat. And they got about 20% more income because they were able to maximize the protein of wheat, because protein in wheat is extremely important for baking quality. In other words, with low protein wheat, your bread just doesn't rise, and it just is very unappetizing that way.
My name is Matt Larson. I am the Associate Director for Climate and Land Use Change at the U.S. Geological Survey. My talk today was about how we use Landsat data to manage water resources, or to improve water resources management. In particular, it was about the instrument called the thermal infrared sensor on Landsat, which allows us to measure heat and energy and moisture flux off the surface of the Earth. So it allows us to measure evapotranspiration. Those images that you saw help us to better understand how much water is being applied to agricultural fields, particularly in the western states where irrigated agriculture is predominant. And it's very important to have good information about how much water is being used by a field so that you can allocate water effectively. Water is scarce in the West. It's highly fought over. States sue each other, counties sue each other, farmers sue each other, and so you need to know very well how much water you're using in a given area so that you can divide up that resource. And so the Landsat images help inform that in a broad way, or so rather than a single measurement made at a farmer's field, you can get a measurement over 100 square, or a square of the Earth's surface 100 by 100 miles. So when you look at a Landsat image, you're seeing actually a number of different what are called spectral bands. So these are bands of electromagnetic radiation that are more than just what the eye sees. So what you and I see is something called, you may remember Roy G. Biv, red, orange, yellow, green, blue, indigo, violet from school. Those are in the visible spectrum of light. But Landsat also measures additional bands of light, infrared and near-infrared, and those allow us to see other types of imagery. So when you see a landscape colored red, that's a different part of the spectral band, not visible with the human eye, but the red shows green vegetation in false color. And it happens that that band is a very good measure of how healthy a vegetated surface is, whether it's a canopy of trees or an agricultural field. So that gives us a measure, or an ability to very well measure the status of a forest, of an area in agriculture, a mangrove coast in the tropics. As temperatures have warmed in the West over the recent decades, we're seeing the pine bark beetle expand its habitat further and further north. And so you can use a Landsat image to see where forests are either unhealthy or actually dead from this infestation. Gives a very precise way to measure that, measure the progress, measure the extent of that beetle, and we're seeing it all the way up into Canada now, unfortunately.
My name is Marcia McNutt. I'm director of the U.S. Geological Survey. I think the beauty of Landsat is that it is an unbiased observer of our planet, and it's been telling us what the planet has been, how it's been changing over the last 40 years. And there's no filter in how we present the Landsat data. It just is what it is. So when people download the Landsat data, it tells them without any interpretation how the planet has changed in response to man's actions. The most important thing about a time series like Landsat is that it gets more valuable rather than less the longer it persists. So every year that Landsat stays in orbit and every additional scene that it captures, the value of Landsat increases. As we continue to stress the water supplies and the food supplies and the living space on this planet, we are going to increasingly turn to Landsat to help guide us in wiser use of the planet.
I'm Tom Loveland. I'm a senior scientist in remote sensing at the USGS AROS Center in Sioux Falls, South Dakota. AROS is an acronym that stands for Earth Resources, Observation, and Science. And it's the central location for the archiving and distribution of Landsat. An image is a permanent record, an historical record of the condition of the Earth at a given point in time. And at Landsat's resolution, at about 30 meters, which is enough to see the fields we managed, the forest that we walk through or harvest, the cities that we live in. Landsat lets us see the extent of those resources and, with that resolution, the condition of them. And so as we look at an image, it gives us the opportunity to detect the kinds of things our eyes see as we wander through the landscape. Only by looking at it from that vertical perspective of space, it's allowing us to see not just a single point, but hundreds of miles at a time. And so we can understand how the slopes are more affected by insect damage in a forest than, say, the flatter areas, or how different parts of agricultural fields are more productive or less productive. It gives us that synoptic, permanent look at how things are.